time has always been one of the most mysterious elements in human thought. We measure it, we live through it, and we sense its passing every second of our lives. Yet when we turn to physics, time becomes far more than just the ticking of a clock or the rhythm of a heartbeat. In physics, time is treated as a measurable dimension, one that is woven into the very fabric of reality alongside the three familiar dimensions of space. To understand why time seems to move in one direction and not the other, we must begin by asking what time truly is and how science has tried to define its flow. From the perspective of relativity, time is not an independent backdrop against which the universe unfolds. Albert Einstein showed that space and time are inseparably joined into a four-dimensional continuum known as space-time. Events do not simply occur in space or in time, but in space-time, and the way we measure intervals between them depends on the motion of the observer. This means that time is not absolute, but relative to the state of motion. A moving clock ticks more slowly than one at rest, and a clock near a massive body ticks more slowly than one far from gravitational influence. Yet despite this relativity, time still seems to carry an unmistakable direction. We remember yesterday, but not tomorrow. We grow older, never younger. Heat spreads out, but does not spontaneously concentrate. The great question that physics faces is why this directionality exists at all. The most familiar explanation comes from thermodynamics. In the 19th century, scientists realized that physical systems have a property called entropy, a measure of disorder, or the number of microscopic ways a system can be arranged. The second law of thermodynamics states that in a closed system, entropy tends to increase. This is why a cup of hot tea left on a table cools down as heat spreads to the air, and why shattered glass does not reassemble itself. The increase of entropy defines what is called the thermodynamic arrow of time. It tells us why the future is different from the past. The universe itself, from its earliest moments after the Big Bang to its present vast expansion, has been following this thermodynamic law. But there are other arrows of time that help define our perception of direction. The psychological arrow refers to the way we experience time in our minds. We form memories of the past, but never of the future. Neurological processes in the brain depend on irreversible physical changes, such as the firing of neurons and the strengthening of synapses, all of which follow the thermodynamic arrow. In this sense, our personal perception of time is anchored to the increase of entropy around us. We cannot recall the future because it has not yet left a physical trace in our brains. Another arrow appears in the way radiation behaves. When we switch on a light, electromagnetic waves spread outward from the source. They do not spontaneously converge from the surrounding space into the bulb. This one-way flow of radiation is called the radiative arrow of time. It arises because waves typically begin from localized sources and spread into wider regions. Mathematically, the equations of electromagnetism allow both forward spreading and inward converging solutions. But in practice, we only see the outward case. This asymmetry adds to our sense that the world has a preferred temporal direction. Together, these arrows paint a picture of time that is not simply an abstract coordinate, but an experienced reality. Thermodynamics explains why processes are irreversible. Psychology explains why our minds perceive time in one direction, and radiation shows us asymmetry in physical propagation. Yet all these arrows are pointing the same way, aligned with what we call the forward march of time. This consistency across so many phenomena is striking, but it also raises a profound question. If the arrows of time are not dictated by fundamental physical laws alone, could there be other realms, other possible universes, where the arrows point in the opposite direction? Could there be domains of reality where entropy decreases, where memory traces lead into what we call the future, and where radiation flows inward instead of outward? The possibility challenges everything we know about experience and causality. To explore it, we must look at the foundations of physics itself. Are the fundamental equations truly one way, or do they in fact allow time to be reversed without contradiction? The journey to answer that will take us deeper into mechanics, quantum theory, cosmology, and philosophy. But it begins here, with the recognition that what we take as the flow of time may be a reflection of particular conditions, not a universal law. When we look at the way physics treats time, we encounter a remarkable contrast between fundamental equations and everyday experience. At the level of Newton's mechanics, Maxwell's equations for electricity and magnetism, or the Schrödinger equation in quantum mechanics, the laws of nature are symmetric with respect to time. In other words, if we were to film a billiard ball rolling on a frictionless table and then play the film backward, the motion would still appear to obey the same rules. Nothing in Newton's laws forbids reversing velocities and retracing the path. The same is true for the behavior of electromagnetic fields or the evolution of a quantum wave function. On paper, time could move either way without contradiction. But when we zoom out to the macroscopic world, the difference is unmistakable. Glass shatters, but does not unshatter. Smoke disperses, but never gathers back into a neat column. Heat flows from hot to cold, not the other way around. What accounts for this enormous gap between the reversibility of fundamental equations and the irreversibility of daily phenomena? The answer lies in probability and the extraordinary number of microscopic components involved in real systems. The second law of thermodynamics emerges from statistical reasoning. Imagine a container of gas, with countless molecules bouncing around at high speed. Each molecule follows reversible Newtonian trajectories, yet when we consider the overall distribution, the system is vastly more likely to be in a disordered state than in an ordered one. There are far more ways for the molecules to spread out than to cluster neatly in one corner. So while the laws permit both directions, probability ensures that we overwhelmingly see entropy increase. In this sense, the arrow of time is not hard-coded into the equations but arises from the collective behavior of matter under specific initial conditions. This realization was one of the great achievements of Ludwig Boltzmann, who introduced statistical mechanics to connect microscopic laws with macroscopic thermodynamics. Boltzmann argued that entropy is a measure of the number of microscopic configurations consistent with a given macroscopic state. High entropy corresponds to disorder because disorder can be achieved in many more ways than order. For example, there is only one way for a deck of cards to be in perfect sequence, but countless ways for it to be shuffled. When you shuffle, you almost certainly move toward disorder, not away from it. The same logic applies to the molecules in a gas or the atoms in a cup of coffee cooling on a table. Yet even here, the situation is not absolute. Theoretically, nothing prevents a rare fluctuation from decreasing entropy. In fact, if you wait long enough, statistical mechanics predicts that such a fluctuation will occur, though the waiting time is fantastically longer than the age of the universe. This brings us to the Poincaré recurrence theorem, which states that a system with finite energy and volume will eventually return arbitrarily close to its initial state. If you could wait an inconceivably long time, a cooled cup of coffee might spontaneously become warm again, as molecules accidentally align. But the timescales are so immense that for all practical purposes, such events will never be observed. The arrow of time, then, is a matter of overwhelming probability, rather than absolute prohibition. Our psychological arrow depends on these same principles. Memory relies on physical records, from synaptic connections in the brain to written words on paper. All these records are formed through processes that increase entropy. When we recall yesterday, it is because yesterday has left a trace, an imprint etched into the present through irreversible changes. Tomorrow has left no such imprint. From within our own minds, time is therefore inseparable from entropy. If entropy were to decrease, our very sense of memory and causality might be inverted. Inhabitants of such a world would not know it as strange. They would simply experience their own arrow as natural, just as we do. The radiative arrow also raises subtle questions. Maxwell's equations are time reversible, meaning they allow solutions where radiation converges into a source just as easily as it spreads outward. Yet we only ever see the spreading solutions. Why? The answer seems to lie in boundary conditions. In our universe, stars shine outward, lamps glow outward, and antennas radiate outward, because these processes start with localized events and spread energy into larger regions. Converging waves would require an incredibly fine-tuned arrangement of the environment to funnel radiation back into the source. Nothing forbids it mathematically, but the initial conditions of our cosmos simply did not provide such tuning. This again highlights that the arrow of time emerges from how the universe began rather than from an absolute law of physics. When we step back, we find that all the arrows of time known to science, thermodynamic, psychological, radiative, are deeply intertwined. They are not independent, but mutually reinforcing. Entropy increases, allowing records to be formed, which shape our perception of time. Entropy increases, setting the conditions under which radiation spreads outward. The arrows line up because they all trace back to the same origin, the initial conditions of the cosmos itself. This insight points us directly toward cosmology, where the great puzzle of time's direction may ultimately be answered. Why did the universe begin in such a low entropy state? And could there be other beginnings that lead to other arrows of time, pointing the other way? To understand why our universe has such a well-defined arrow of time, we must examine the role of cosmology. The most compelling explanation is that the universe began in a state of extremely low entropy. This is a surprising fact because if we imagine all the possible ways matter and energy could have been arranged at the birth of the cosmos, a low entropy configuration is extraordinarily unlikely. Yet the Big Bang, the event that launched the universe nearly 14 billion years ago, seems to have done exactly that. The early universe was astonishingly smooth, with matter and radiation distributed almost evenly across space, interrupted only by tiny fluctuations. Smoothness corresponds to low entropy because it represents a very special arrangement among the vast set of possible configurations. As the universe expanded, gravity amplified those small fluctuations, pulling matter together into galaxies, stars, and planets. From the standpoint of entropy, this represented an increase. Structures formed, stars ignited, and energy began flowing in organized ways. On Earth, this flow of energy from the sun allowed life to emerge, and with it the human sense of time. All of it traces back to the peculiar fact that the universe began in a state of extraordinary order. Without that, there would be no thermodynamic arrow, no memories, and no perception of a flowing time. Why the universe began this way remains one of the deepest mysteries of modern physics. Some scientists suggest it is simply a brute fact, something we must accept without explanation. Others propose that it is tied to the laws of quantum cosmology, where the probabilities of different initial states might favor low entropy beginnings. Still, others speculate that our universe may be one of many, with different regions or cycles exhibiting different arrows of time depending on their own starting points. The philosopher Thomas Gold once argued that in a collapsing universe, the arrow of time might reverse, so that entropy would decrease as the universe approached its end. Later, cosmologists such as Sean Carroll and Jennifer Chen proposed that if new universes emerge out of quantum fluctuations in a larger multiverse, each could have its own arrow. In such a picture, universes might be born in pairs, one with time flowing as we perceive it, and the other with time flowing in the opposite direction. From within either universe, inhabitants would see their own arrow as normal, never realizing that another cosmos runs in reverse. This way of thinking shifts the puzzle from being about absolute laws to being about conditions. The fundamental equations of physics allow for symmetry, permitting time to run either way. What breaks that symmetry is how a universe begins. In our case, the beginning was highly ordered, and entropy has been climbing ever since. In a mirror case, the beginning might have been highly ordered in the opposite sense, leading entropy to increase in the other direction. Both outcomes are consistent with the mathematics. The psychological consequences are staggering. If you lived in a universe where entropy decreased toward what we call the future, you would not perceive your life as moving backward. Your memories would still form along the arrow of entropy. You would remember what we consider the future and forget what we consider the past. For you, time would flow forward, exactly as it does for us. The very notion of forward and backward has meaning only relative to the arrow of entropy. What feels like reversal to us would feel like normalcy. To them, the radiative arrow would also be inverted. In such a cosmos, waves would converge into sources rather than spread outward. light bulbs would not glow into a room, but instead appear to gather light from the walls. Yet to the inhabitants of that world, it would not appear strange at all. Their expectations would be shaped by the same conditions that shape ours. For them, the universe would be no less natural. This perspective highlights an important truth. The arrows of time we know are not universal decrees, but contingent results of how our universe began. They are emergent features, not fundamental constants. Our sense of time flowing forward, from past to future, is deeply tied to entropy, radiation, and memory, all of which spring from the same low-entropy origin of the cosmos. If we dare to imagine universes with different beginnings, then the possibility of different arrows of time cannot be dismissed. As we close this first chapter, we are left with a profound realization. Time, as we live it, is not guaranteed by the deepest laws of physics. It is a story written by the peculiar initial conditions of our universe. The thermodynamic arrow, the psychological arrow, and the radiative arrow all align in our world, pointing forward together. But nothing in the mathematics forbids them from pointing the other way under different conditions. And so, the question arises, one that will guide us through the journey ahead. If our universe is only one of many possible realities, could there be others where the arrows of time point differently? Could there truly exist universes in which everything unfolds in reverse, yet feels to their inhabitants just as real as it does to us? At first glance, the world around us seems completely irreversible. A glass that slips from a hand shatters into pieces that never leap back together. A drop of ink spreads through water and never spontaneously gathers again. Heat flows from a hot object to a cold one, and not the reverse. These examples shape our everyday understanding of time as a one-way passage. Yet when we turn to the foundations of physics, we find something unexpected. The fundamental equations that describe motion, fields, and quantum states do not care about direction. They work just as well backward as forward. Consider the mechanics formulated by Isaac Newton in the 17th century. Newton's laws of motion allow us to predict the trajectory of a planet or the swing of a pendulum. If we were to record a pendulum's swing and then play the recording backward, the motion would still obey Newton's equations. The same is true for the orbits of planets or the paths of billiard balls colliding on a frictionless table. The laws are time reversible because they depend only on acceleration and forces, not on whether the clock is ticking forward or backward. In the 19th century, James Clerk Maxwell unified electricity and magnetism with his famous equations. These two are time symmetric. If we swap the direction of time, the electric and magnetic fields evolve in a way that remains entirely consistent with the mathematics. The propagation of electromagnetic waves outward from a source could just as easily be described in reverse, with waves converging into the source. The equations themselves do not break the symmetry. It is only the actual boundary conditions in our universe that make one direction overwhelmingly more likely. Quantum mechanics, which governs the smallest scales of nature, follows the same pattern. The Schrödinger equation, which describes how the wave function of a particle evolves, is perfectly symmetric with respect to time. If we replace time with its negative, the equation remains valid. In fact, Richard Feynman famously showed that the mathematics of quantum field theory could be interpreted as particles moving forward in time or as antiparticles moving backward in time. From this perspective, antimatter is simply matter seen with time reversed. This raises a striking puzzle. If the fundamental laws of physics do not distinguish between past and future, then why does our experience of the world insist on the arrow of time? Why do we see entropy rise, heat dissipate, and causes precede effects when nothing in the equations demands it? The contrast between microscopic reversibility and macroscopic irreversibility is one of the deepest tensions in science. To approach this question, physicists have examined the role of initial conditions. Suppose we film two billiard balls colliding on a frictionless surface. If we play the film backward, the reversed motion is just as plausible. The reason is that the system is simple, involving only a few degrees of freedom. But if we film a glass of water shattering, the backward sequence looks absurd. That is because the system involves an enormous number of microscopic particles. In principle, the reversed motion is possible, but it would require a fantastically precise alignment of the positions and velocities of all the atoms involved. Without such fine-tuning, the forward direction, where entropy increases, is overwhelmingly favored. This difference highlights that the arrow of time is not written into the fundamental laws, but emerges from the conditions of the universe and the collective behavior of vast numbers of particles. The laws give permission for time to run both ways. What chooses the actual direction is the state in which the universe begins. The special low-entropy conditions of the early cosmos tipped the balance, setting everything on the path we now call forward. In this sense, the irreversibility we see around us is a kind of illusion, or rather, a feature of scale. At the level of molecules, electrons, and photons, time has no preferred direction. At the level of shattered glass and cooling stars, direction emerges because of probability. This delicate interplay between reversible laws and irreversible phenomena has shaped physics for centuries, and it continues to drive some of the most profound debates in modern cosmology. When we examine nature more closely, the contrast between reversible laws and irreversible outcomes becomes even sharper. Take the case of a container filled with gas molecules. Each molecule obeys Newton's laws, colliding elastically with others, conserving energy and momentum in a perfectly reversible fashion. If you were to reverse the velocities of every single molecule at once, the entire system would retrace its history precisely, eventually returning to its original state. The mathematics allows it, and nothing in the microscopic dynamics would prevent it. Yet, in practice, this never occurs. The gas always spreads evenly, entropy always rises, and the process never spontaneously reverses. The reason is probability. In a system of a few particles, arranging them into a precise state is conceivable. But in a system of trillions upon trillions of particles, the chance that they all just happen to arrange themselves into a lower entropy state is unimaginably small. To put this into perspective, consider the air in the room around you. It is possible, by the strict laws of physics, that every molecule of air could suddenly cluster into one corner of the room, leaving the rest of the space in a vacuum. Yet the odds of this happening are so staggeringly low that it would never occur within the lifetime of the universe. The overwhelming probability is that the molecules remain spread out, defining the arrow of time through the inexorable increase of entropy. This statistical nature of irreversibility was at the heart of Ludwig Boltzmann's work in the 19th century. Boltzmann proposed that entropy is not a mysterious tendency toward disorder, but a mathematical expression of probability. He wrote entropy as proportional to the logarithm of the number of microscopic configurations consistent with a macroscopic state. A highly ordered state, such as a new deck of cards in perfect sequence, corresponds to only one arrangement. A disordered deck corresponds to an astronomical number of possible arrangements. That is why shuffling almost always increases disorder. The same logic applies to the dispersal of gases, the cooling of hot objects, and the spreading of radiation. The underlying equations are reversible, but probability makes one direction dominate. This leads to a profound realization. The arrow of time that we experience is not imposed by the equations of physics, but by the conditions under which those equations play out. If we could set up the universe with reversed initial conditions, entropy would decrease, and time as experienced by its inhabitants would flow in the opposite direction. From within that universe, it would feel just as natural and irreversible as our own. The reversibility of the fundamental laws is also evident in the behavior of light and radiation. Maxwell's equations allow for both retarded solutions, where radiation spreads outward from a source, and advanced solutions, where radiation converges inward. In practice, we only see the outward case. But this is not because the equations forbid the inward case. Rather, it is because the universe, as a whole, began with conditions that overwhelmingly favor outward radiation. If the initial state of the cosmos had been arranged differently, perhaps converging radiation would be the norm. Once again, the equations remain neutral, while the initial conditions choose the direction. Even in quantum mechanics, Reversibility lies at the heart of the equations. The Schrödinger equation evolves a wave function smoothly in time, and if we reverse the sign of time, the evolution is still valid. It is only when we perform a measurement that the situation appears asymmetric. The so-called collapse of the wave function seems to mark a before and after, as if time has a definite flow, but many interpretations of quantum theory argue that this collapse is not a fundamental process, but an effective description of interaction with the environment. When considered as a whole, the quantum world remains time-symmetric. The contrast becomes clearer when we compare microscopic reversibility with macroscopic irreversibility. At the microscopic level, there is nothing to distinguish past from future. At the macroscopic level, the distinction is overwhelming. The smoke from a fire disperses and never regathers. A broken egg never reassembles. The bridge between these levels is probability, amplified by the sheer number of particles involved. What looks like a hard law at our scale is, at its foundation, an expression of overwhelming likelihood rather than impossibility. This raises the central paradox of time. The fundamental equations tell us that past and future are mirror images, equally valid directions. But our experience, and the second law of thermodynamics, insist that the future is different from the past. How can both be true? The resolution lies in understanding that the equations describe what is possible, while the initial conditions of the universe determine what is actual. Physics permits both directions, but the cosmos we inhabit began in such a way that only one direction became dominant. The mystery of time's arrow ultimately points us toward the beginning of the universe itself. If the equations of physics allow both directions equally, then what decided that our cosmos would evolve in the way it has? The most convincing answer lies in the boundary conditions at the start. The universe began in a state of extraordinarily low entropy, smooth and finely balanced, with matter and energy spread nearly uniformly. From that improbable foundation, entropy could only rise, and the direction we call forward was set. Without that special beginning, the arrows of time would not exist in their present form. This understanding transforms how we think about irreversibility. What seems like a deep law of nature is in fact the unfolding of initial conditions across vast scales. The second law of thermodynamics is not a command written into the equations, but a reflection of how the universe was arranged at its birth. That arrangement determined not only the flow of heat and the increase of entropy, but also the way memories form in brains, the way radiation propagates, and the way we perceive cause and effect. Our sense of time's direction is inseparable from the initial conditions of the cosmos. To illustrate this, imagine rewinding the universe. If we could reverse the velocities of every particle in existence, the cosmos would retrace its steps, galaxies would collapse, stars would unburn, and all processes would run in reverse. The laws of physics would have no objection. But the precision required to arrange such a reversal is so absolute that it could never be achieved in practice. One misplaced atom would spoil the sequence, and entropy would rise again. The forward direction wins, not because it is the only possible one, but because it is the overwhelmingly stable outcome given the universe we have. This insight also explains why we never see macroscopic violations of the second law. While the equations permit rare fluctuations, the probabilities are so tiny that they are effectively invisible on human timescales. The recurrence times required for a system to return to a low entropy state are measured not in years or millennia, but in numbers so vast they dwarf imagination, far longer than the age of the universe. For us, and for all practical purposes, entropy always increases. Yet the deeper message is that nothing in the laws themselves forbids a different outcome. If another universe were to begin with reversed initial conditions, its arrow of time could run the other way. For the beings living there, memory, radiation, and entropy would all align with that reversed flow. They would never think of themselves as moving backward. Their world would feel as natural and forward-flowing as ours. The reversibility of the fundamental laws leaves open the possibility of such universes, even if we cannot observe them directly. This brings us to a profound turning point. The everyday irreversibility we take for granted is not the deepest truth about nature. Beneath it lies a symmetry that permits both directions of time equally. What we experience is the result of a cosmic choice, set at the origin of everything. If the conditions had been different, our arrow could have pointed another way. As we leave this chapter, we carry with us a crucial realization. The arrow of time is not dictated by Newton's mechanics, by Maxwell's equations, or by the Schrödinger equation. It is dictated by the special state in which the universe began. Physics itself does not forbid reversal. It is only our particular history that makes forward feel inevitable. This realization opens the door to a startling possibility. If time's direction is not absolute, then other universes might exist where it is reversed. To explore that possibility, we must now turn to entropy, statistics, and the question of why irreversibility dominates in practice. To understand why the arrow of time arises so consistently in our universe, we must take a closer look at entropy itself. Entropy is one of the most important concepts in all of physics, yet it is often misunderstood. It is sometimes described as disorder, sometimes as randomness, and sometimes as a measure of ignorance about microscopic details. Each description captures part of the truth, but none fully explains why entropy is central to the direction of time. The story begins in the 19th century, when scientists were trying to connect the macroscopic laws of thermodynamics with the microscopic world of atoms and molecules. Thermodynamics had already established the second law, which states that entropy in a closed system never decreases. But why should this be true? To answer, Ludwig Boltzmann developed statistical mechanics, a framework that linked the behavior of vast numbers of particles to the familiar laws of heat and energy. Boltzmann's key insight was to recognize that entropy corresponds to the number of microscopic configurations consistent with a macroscopic state. Imagine a box of gas. At the macroscopic level, we can describe its temperature, pressure, and volume. But at the microscopic level, each molecule has a precise position and velocity. There are countless ways for those molecules to arrange themselves while still producing the same temperature and pressure. Boltzmann defined entropy as a measure of this multiplicity. The more microstates available, the higher the entropy. From this perspective, entropy increase is simply the tendency of systems to move towards states with more possible micro-configurations. A shuffled deck of cards illustrates the point. There is only one way for the deck to be in perfect order, but there are enormously many ways for it to be shuffled. Thus, when you shuffle, you almost inevitably move toward higher entropy. The same logic applies to gases mixing, ice melting, and stars burning their fuel. It is not that nature prefers disorder, but rather that disorder is vastly more probable than order. Boltzmann even inscribed his famous equation for entropy on his gravestone. Entropy equals a constant multiplied by the logarithm of the number of microstates. This equation captures the statistical essence of the second law. It shows that irreversibility is not a matter of strict prohibition, but of overwhelming probability. Systems evolve toward higher entropy because those states dominate the landscape of possibilities. Yet this reasoning gave rise to a troubling question, known as Loschmidt's paradox. If the microscopic laws of motion are reversible, then why should entropy ever increase? If one could reverse all the velocities of the molecules in a gas, the system would move back toward a lower entropy state, seemingly violating the second law. The paradox highlights the tension between microscopic reversibility and macroscopic irreversibility. Boltzmann responded that while such reversals are possible in principle, they require conditions so precise that they are never realized in practice. Random interactions always push the system toward more probable states, and those states almost always mean higher entropy. Another challenge comes from the Poincaré recurrence theorem, which states that a finite system will eventually return to a state arbitrarily close to its starting point if given enough time. This implies that entropy could decrease after unimaginably long intervals. Boltzmann acknowledged this, but argued that the timescales involved are so vast that they exceed any conceivable observation. The recurrence times for a system the size of the universe are larger than numbers we can meaningfully write down. For all practical purposes, entropy still increases. The brilliance of Boltzmann's approach lies in recognizing that the arrow of time is not written into the fundamental laws, but emerges from statistics. It is not that entropy cannot decrease, but that it almost never does. The direction of time we experience is a reflection of overwhelming probability. This insight connects the second law directly to the initial conditions of the universe. Because the cosmos began in a state of low entropy, it had only one way to evolve: toward higher entropy. Our arrow of time is thus a story written by the initial state and the inexorable logic of statistics. But the paradoxes remain important, because they show that irreversibility is not absolute. Loschmidt's paradox reminds us that reversal is always permitted in principle, and the recurrence theorem shows that even decreases of entropy are not forbidden, only fantastically unlikely. Together, they highlight that the arrow of time is not a law imposed from above, but an emergent property, deeply tied to probability and the conditions of the cosmos. Entropy becomes even more fascinating when we confront its paradoxes head-on. Joseph Loschmidt, a physicist who admired Boltzmann's work yet remained skeptical, posed one of the sharpest challenges. He pointed out that if the laws of motion are reversible, then for every process that increases entropy, there must exist a corresponding process that decreases it. If you could take a film of gas molecules spreading evenly through a container and reverse every molecular velocity at a single instant, the gas would collapse back into one corner, reducing entropy. This thought experiment is entirely consistent with Newton's mechanics. How, then, can the second law claim that entropy never decreases? Boltzmann responded by emphasizing probability. While the reversal is possible, arranging such precise conditions is effectively impossible without outside intervention. The natural jostling of molecules through collisions ensures that any small error in reversing velocities will grow rapidly, pushing the system back toward higher entropy states. This is an early recognition of what we now call sensitivity to initial conditions, a property that underlies chaos theory. In practice, entropy increase is guaranteed not because decrease is forbidden, but because decrease requires an unimaginably unlikely fine-tuning of the microscopic details. A second challenge came from the Poincaré recurrence theorem, proved in the late 19th century. The theorem states that in a finite system with fixed energy, the system will, after a sufficiently long but finite time, return arbitrarily close to its initial state. For a gas in a box, this means that given enough time, the molecules would spontaneously cluster back into one corner, reversing entropy. The catch is that the recurrence time grows exponentially with the number of particles. For a system the size of the universe, the recurrence time is longer than 10 to the power of 10 to the power of 100 years, a number so vast it defies comprehension. On such scales, recurrence is effectively irrelevant. Entropy still appears to increase, without exception. These paradoxes reveal the subtlety of the second law. It is not an ironclad rule carved into the structure of physics. It is a statement of near certainty, a law of overwhelming probability. Irreversibility is statistical, not absolute. This distinction matters because it shows that the arrow of time is contingent on the conditions of the system and the cosmos, not on a fundamental asymmetry in the equations. From this perspective, we can see why entropy is intimately tied to the beginning of the universe. If the cosmos had begun in a high entropy state, there would be no arrow of time, no growth of disorder, and no sense of past and future. The fact that the early universe was so smooth, so low in entropy, set the stage for everything that followed. As gravity amplified small fluctuations, entropy increased, creating stars, galaxies, and eventually the environments in which life could emerge. The arrow of time is the shadow of this rise in entropy, stretching from the Big Bang to the present moment. This reasoning also explains why we remember the past, but not the future. Records, whether they are footprints in sand or synapses in a brain, are formed through irreversible processes that increase entropy. The past is fixed because it has left physical traces. The future is open because it has not yet done so. If entropy were to decrease instead, our sense of memory would reverse. We would recall what we call the future, and forget what we call the past. The direction of psychological time is therefore inseparable from the statistical nature of entropy. It is striking to realize how much of human experience, from the cooling of a cup of coffee to the arrow of memory itself, depends on statistical laws. We do not experience time flowing forward because the equations of physics demand it, but because the universe began in an improbable state and has been evolving probabilistically ever since. What feels like necessity is in fact overwhelming likelihood. The second law is not a chain that binds the universe, but a tide that sweeps it in one direction, simply because the alternative is too improbable to be seen. The link between entropy and the universe itself takes us to the heart of modern cosmology. If the second law is statistical rather than absolute, then its power lies in the initial state of the cosmos. The fact that entropy is increasing today means it must once have been low. But why should the universe have begun in such a special, highly ordered condition? Out of all the possible arrangements of matter and energy, the vast majority would correspond to high entropy states. The early cosmos, instead, was astonishingly smooth, with matter and radiation spread nearly uniformly, interrupted only by slight fluctuations at the level of 1 part in 100,000. This smoothness was not randomness, but order, and it allowed entropy to grow from that point forward. The mystery is deepened when we consider gravity. Unlike most forces, gravity does not favor smooth distributions. A gas left to itself will spread evenly, but matter under gravity clumps together. For a gravitational system, disorder corresponds not to smoothness, but to inhomogeneity, to collapsed structures like black holes. From this perspective, the early universe was in an incredibly special low-entropy state because it was so uniform. It had enormous potential for entropy to grow by forming stars, galaxies, and eventually black holes, which represent some of the highest entropy objects known. Boltzmann himself speculated on these questions. He proposed that perhaps our universe is a rare fluctuation within a much larger system, a temporary pocket of low entropy carved out of a sea of high entropy. This idea, though imaginative, led to puzzles of its own. If fluctuations are the explanation, then smaller fluctuations are more probable than larger ones. It would be far more likely, for instance, for a single brain to fluctuate into existence than for an entire universe like ours to appear. This so-called Boltzmann brain problem shows that explaining our arrow of time by random fluctuation alone cannot be sufficient. Modern cosmology has taken a different approach. The inflationary model suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion that smoothed out irregularities and set the stage for low-entropy initial conditions. While the details remain uncertain, this framework shows that the peculiar beginning of the cosmos might be explained by physical processes rather than sheer chance. What matters for our understanding of time is that the smoothness of the early universe is the reason entropy could rise, and thus the reason we experience time as flowing forward. The Poincaré recurrence theorem reminds us that over inconceivably long times, entropy could fluctuate downward, and Loschmidt's paradox reminds us that reversal is always allowed in principle. But both also highlight how improbable such events are. The arrow of time is not absolute, but it is stable over scales that matter to us. It persists because the initial conditions gave it room to unfold. Our entire history, from the birth of stars to the writing of these words, is part of that vast statistical evolution. As we close this chapter, the picture becomes clear. Entropy is not simply disorder or decay, but a statistical measure of probability. It explains why macroscopic processes are irreversible even though microscopic laws are reversible. It connects memory and causality to the physical traces of the past. And it ties the direction of time to the very beginning of the cosmos. Without a low entropy start, there would be no arrow of time, no unfolding history, and no perception of past and future. This realization points us toward an even larger question. If the arrow of time depends on initial conditions, then perhaps other universes, born with different beginnings, might follow different arrows. Could there be realms where entropy decreases, where the psychological and radiative arrows point the other way, and where time itself flows in reverse? To explore such possibilities, We must now turn directly to cosmology and the origins of time's arrow in the structure of the universe. The link between entropy and the universe itself takes us to the heart of modern cosmology. If the second law is statistical rather than absolute, then its power lies in the initial state of the cosmos. The fact that entropy is increasing today means it must once have been low. But why should the universe have begun in such a special, highly ordered condition? Out of all the possible arrangements of matter and energy, the vast majority would correspond to high entropy states. The early cosmos instead was astonishingly smooth, with matter and radiation spread nearly uniformly, interrupted only by slight fluctuations at the level of 1 part in 100,000. This smoothness was not randomness, but order, and it allowed entropy to grow from that point forward. The mystery is deepened when we consider gravity. Unlike most forces, gravity does not favor smooth distributions. A gas left to itself will spread evenly, but matter under gravity clumps together. For a gravitational system, disorder corresponds not to smoothness, but to inhomogeneity, to collapsed structures like black holes. From this perspective, the early universe was in an incredibly special low entropy state, because it was so uniform. It had enormous potential for entropy to grow by forming stars, galaxies, and eventually black holes, which represent some of the highest entropy objects known. Boltzmann himself speculated on these questions. He proposed that perhaps our universe is a rare fluctuation within a much larger system, a temporary pocket of low entropy carved out of a sea of high entropy. This idea, though imaginative, led to puzzles of its own. If fluctuations are the explanation, then smaller fluctuations are more probable than larger ones. It would be far more likely, for instance, for a single brain to fluctuate into existence than for an entire universe like ours to appear. This so-called Boltzmann brain problem shows that explaining our arrow of time by random fluctuation alone cannot be sufficient. Modern cosmology has taken a different approach. The inflationary model suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion that smoothed out irregularities and set the stage for low entropy initial conditions. While the details remain uncertain, this framework shows that the peculiar beginning of the cosmos might be explained by physical processes rather than sheer chance. What matters for our understanding of time is that the smoothness of the early universe is the reason entropy could rise, and thus the reason we experience time as flowing forward. The Poincaré recurrence theorem reminds us that over inconceivably long times, entropy could fluctuate downward, and Loschmidt's paradox reminds us that reversal is always allowed, in principle. But both also highlight how improbable such events are. The arrow of time is not absolute, but it is stable over scales that matter to us. It persists because the initial conditions gave it room to unfold. Our entire history, from the birth of stars to the writing of these words, is part of that vast, statistical evolution. As we close this chapter, the picture becomes clear. Entropy is not simply disorder or decay, but a statistical measure of probability. It explains why macroscopic processes are irreversible, even though microscopic laws are reversible. It connects memory and causality to the physical traces of the past, and it ties the direction of time to the very beginning of the cosmos. Without a low entropy start, there would be no arrow of time, no unfolding history, and no perception of past and future. This realization points us toward an even larger question. If the arrow of time depends on initial conditions, then perhaps other universes, born with different beginnings, might follow different arrows. Could there be realms where entropy decreases, where the psychological and radiative arrows point the other way, and where time itself flows in reverse? To explore such possibilities, we must now turn directly to cosmology and the origins of time's arrow in the structure of the universe. If the arrow of time is a story written by entropy, then its first chapter was set at the birth of the universe. To understand why time flows forward, we must understand why the cosmos began in a state so special, so low in entropy, that the rise of disorder could unfold for billions of years. Cosmology is the stage upon which the arrow of time was defined, and it is within the history of the universe that we find clues to its direction. The modern story of cosmic origins begins with the Big Bang. Nearly 14 billion years ago, the universe emerged from an incredibly hot, dense, and compact state. Space itself expanded, carrying matter and radiation outward. In its earliest fractions of a second, the universe was filled with a nearly uniform plasma of particles and photons. Smoothness was the dominant feature, with only tiny variations in density, measured today as faint ripples in the cosmic microwave background radiation. These ripples, at the level of 1 part in 100,000, would later seed the galaxies, stars, and planets. At first glance, such smoothness might seem like disorder. Yet in the context of gravity, it is precisely the opposite. A smooth universe is a low-entropy universe, because gravity prefers to clump matter into structures. Left unchecked, the gravitational tendency is to form collapsed objects, such as black holes, which represent states of extremely high entropy. In contrast, a perfectly uniform distribution is delicate, balanced, and highly ordered. The fact that the early universe was so smooth means it was born in a low-entropy state. From that improbable beginning, entropy had only one way to go: upward. As expansion progressed, gravity amplified the tiny ripples, pulling matter into clumps. Galaxies formed, stars ignited, and planets took shape. Each step increased entropy by moving the universe toward more probable configurations. The thermodynamic arrow we experience today, from cooling coffee to aging bodies, is ultimately a shadow cast by that ancient expansion and the growth of structure it unleashed. This connection between the Big Bang and the arrow of time was not obvious at first. In the early 20th century, physicists thought of entropy mainly in terms of gases and heat. It was only later, as scientists considered the gravitational dynamics of the cosmos, that the link became clear. A smooth early universe is special because it allowed entropy to rise as structure formed. Without that low entropy beginning, there would be no flow of time as we know it. But this raises one of the deepest puzzles in physics. Why was the early universe so smooth in the first place? Out of all the possible arrangements of matter and energy, almost all would correspond to high entropy. To find the cosmos in such an ordered state seems almost miraculous. Yet it is this smoothness that made everything possible, from the birth of galaxies to the emergence of life. Physicist Roger Penrose has emphasized just how special this beginning must have been. He calculated that the probability of the universe starting in such a low entropy state is astronomically tiny, far smaller than 1 chance in 10 to the power of 10 to the power of 100. Numbers of this scale are beyond ordinary comprehension. The message is that the early cosmos was not just unlikely, but extraordinarily fine-tuned for low entropy. And this fine-tuning is the reason we experience a forward-moving arrow of time. Cosmology, then, is not only about the large-scale structure of the universe, but also about the very possibility of time itself. The expansion of space, the smoothness of the early cosmos, and the amplification of small fluctuations together created the conditions under which entropy could rise. Without them, the second law would have no meaning, and time would have no direction. The expansion of the universe plays a central role in shaping the arrow of time. From the moment of the Big Bang, space itself has been stretching, carrying galaxies apart, and cooling the background radiation. This expansion ensures that entropy has room to grow. Without expansion, the universe would have remained hot and dense, leaving no stage for complexity to emerge. Instead, the stretching of space allowed energy to spread, matter to clump under gravity, and entropy to increase in ways that define the direction of time we experience today. One of the most remarkable ideas in modern cosmology is inflation. According to this theory, in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size again and again at an astonishing rate. Inflation smoothed out irregularities, flattened space, and left behind the nearly uniform conditions we see in the cosmic microwave background. It also provided the seeds of later structure in the form of quantum fluctuations, which were stretched to cosmic scales by the rapid expansion. These fluctuations became the small density variations that gravity later amplified into galaxies and clusters. From the perspective of entropy, inflation performed two critical functions. First, it reset the cosmos into a state of extraordinary smoothness, ensuring a low entropy beginning. Second, it supplied just enough irregularity to allow entropy to rise as structures formed. Without inflation, the universe might have been too clumpy or too chaotic to sustain the arrow of time as we know it. With inflation, the cosmos began with conditions that guaranteed entropy would increase steadily for billions of years. The cosmic microwave background, discovered in the 1960s, provides direct evidence for this story. It is the faint glow left over from the moment the universe cooled enough for atoms to form, about 380,000 years after the Big Bang. Its near uniformity confirms that the early cosmos was smooth, while its tiny fluctuations reveal the seeds of structure. In this radiation, we see both the low entropy origin and the beginning of entropy's rise, frozen in light that has been traveling across space for nearly 14 billion years. The expansion also shapes the long-term fate of the arrow of time. As the universe grows, stars burn their fuel, galaxies drift apart, and energy becomes ever more thinly spread. Entropy continues to rise as systems approach equilibrium. The ultimate future may be a heat death, in which the cosmos reaches maximum entropy and no further change is possible. In such a scenario, the arrow of time would lose its meaning, because nothing would distinguish past from future in a state of perfect equilibrium. Our entire experience of time's flow depends on being in an era when entropy is still rising, far from equilibrium. Cosmologists like Thomas Gold proposed that if the universe were to recollapse in a big crunch, perhaps the arrow of time would reverse, with entropy decreasing as the cosmos contracted. While this idea is elegant, evidence for an eventual collapse has faded. Observations show that the expansion is accelerating, driven by what is called dark energy. Instead of reversing, the universe seems destined to expand forever. The arrow of time, once set by the low entropy beginning, appears to be unidirectional for the entire history of our cosmos. Yet the possibility of time symmetry remains alive in theoretical discussions. Some physicists, including Sean Carroll and Jennifer Chen, have suggested that universes may be born in pairs, with arrows of time pointing in opposite directions. In this view, our universe is not unique, but one half of a larger whole, balanced by a mirror cosmos, where entropy increases toward what we would call the past. From within each universe, the arrow feels natural. From outside, if such a perspective could exist, the two would be mirror images in time. This possibility highlights how expansion, entropy, and initial conditions are deeply intertwined. The universe's growth did more than scatter galaxies and cool radiation. It defined the very direction of time, ensuring that entropy would rise and that history would unfold as we know it. If expansion had been different, or if initial conditions had been less special, the arrow of time might never have existed at all. The great puzzle of cosmology is not only that the universe began, but that it began in such a special way. The smoothness of the early cosmos, confirmed by the cosmic microwave background, represents an initial condition so improbable that it cries out for explanation. Why should the universe start in a state of such low entropy when higher entropy states are vastly more likely? This is the question that has led scientists to explore time, symmetry, and the possibility of universes beyond our own. One approach is to accept the initial condition as a brute fact. Perhaps the cosmos simply began that way, and our arrow of time is an unavoidable consequence. But many physicists find this unsatisfying. They prefer explanations that show how the improbable can arise from deeper principles. Inflation is one attempt, smoothing and flattening the universe in its first moments. Yet even inflation requires its own special conditions to start, and the puzzle is not fully resolved. Another idea, championed by Thomas Gold, is that the universe might be time-symmetric on the largest scales. In his view, if the cosmos were to collapse in a big crunch, entropy could decrease during contraction, effectively reversing the arrow of time. This bold hypothesis sought to preserve symmetry at the grandest level, but as observations now show, the expansion of the universe is accelerating rather than slowing. A big crunch seems increasingly unlikely. Gold's vision may not describe our cosmos, Yet it opened the door to imagining arrows of time that reverse under different conditions. More recently, Sean Carroll and Jennifer Chen proposed that time symmetry could emerge not from a collapsing cosmos but from the birth of multiple universes. In their model, a larger multiverse can spawn baby universes through quantum fluctuations. Each new universe begins with its own arrow of time, determined by its initial conditions. Some universes, like ours, have entropy that increases in the direction we call forward. Others could have entropy that increases in the opposite direction. From the standpoint of physics, both are equally valid. From within each universe, the arrow feels natural, while from outside, the pair would appear as mirror images in time. This picture offers a striking resolution to the puzzle of initial conditions. Instead of demanding that the cosmos begin in a uniquely improbable state, it allows for many universes, each with different beginnings. Among them, some will naturally have low entropy starting points that give rise to arrows of time. We inhabit one such universe, while others may exist with arrows pointing in reverse. The laws of physics are symmetric, but the multiverse ensures that both outcomes are realized. The implications are profound. If universes can exist with arrows of time pointing in opposite directions, then time itself is not a universal property but a local one, emerging differently in different domains of reality. Our sense of past and future is not absolute but contingent, tied to the history of our own cosmos. In another universe, beings may look back on what we call our future and see it as their past. For them, memory, causality, and radiation all flow in the opposite direction, yet feel just as real and natural. Cosmology therefore teaches us that time's arrow is not inevitable. It is the product of conditions, smoothness, expansion, and the amplification of fluctuations. Our universe happens to have one arrow, but others could exist with the opposite. The deep symmetry of physical law allows it, and the vastness of the multiverse makes it plausible. As we close this chapter, we are left with a new perspective. Time's arrow is not written in the equations, but in the universe's beginning. The low entropy of the Big Bang, the expansion of space, and the growth of structure together created the flow we experience. Yet beyond our cosmos, other flows may exist, equally valid, equally real. The mystery of time is therefore inseparable from the mystery of cosmology. To go further, we must step beyond our universe and ask how the multiverse itself might host different arrows of time. The realization that the arrow of time depends on the initial conditions of the universe naturally leads to a deeper question. If our cosmos began in a special state, is it possible that other universes began differently, with arrows pointing in other directions? This possibility takes us into the realm of the multiverse, the idea that reality may contain not just one universe but many, each with its own laws, histories, and arrows of time. Though speculative, multiverse models arise directly from well-established theories in cosmology and particle physics. One of the most influential frameworks is eternal inflation. Inflation, the rapid expansion that smoothed the early universe, may not have been a one-time event. Instead, it could be an ongoing process in which regions of space continue to inflate even today. In this picture, bubbles of space stop inflating and form universes like ours, while the background continues to expand eternally. Each bubble becomes a separate cosmos, isolated from the others by the ever-growing space between them. The result is a multiverse, a vast collection of universes, each born with its own conditions. Within eternal inflation, the initial state of each bubble determines its arrow of time. Some bubbles may start smooth and low in entropy, as ours did, giving rise to a forward-pointing arrow. Others may begin in different states, perhaps allowing entropy to increase in the opposite direction. Because the laws of physics are symmetric, there is no reason why only one direction should occur. The multiverse provides the stage for both. Another perspective comes from string theory, which suggests that the fundamental building blocks of nature are tiny vibrating strings. String theory predicts an enormous landscape of possible vacuum states, each corresponding to a different version of physical law. The number of possibilities may be as large as 10 to the power of 500. If each vacuum gives rise to its own universe, the multiverse becomes a vast mosaic of realities. Among this enormous variety, arrows of time could differ depending on how each universe begins. A crucial piece of the puzzle comes from the principle of symmetry in particle physics. The combined symmetry of charge, parity, and time reversal, known as CPT, symmetry, is one of the most fundamental features of quantum field theory. CPT symmetry states that if we invert charge, flip spatial coordinates, and reverse time, the laws of physics remain unchanged. This powerful symmetry suggests that for every process moving forward in time, an equally valid process exists, moving backward. If our universe embodies one direction, a mirror universe could embody the opposite, with CPT symmetry linking the two. Physicists such as Julian Barber and Neil Turok have explored models in which universes are born in pairs, emerging from a shared origin, but evolving with arrows of time pointing away from each other. In these scenarios, the Big Bang is not the beginning of time, but a central dividing point. On one side lies our universe, with entropy increasing toward what we call the future. On the other side lies a mirror universe, with entropy increasing in the opposite direction. To inhabitants of either cosmos, time feels natural and forward. From the outside, the two are perfectly symmetric. This vision reframes the puzzle of time. Instead of asking why our universe began with low entropy, we ask whether low entropy beginnings are inevitable when universes are born in pairs. In such a framework, time symmetry is preserved on the largest scale, even as individual universes experience time in one direction. The multiverse becomes a theater where arrows of time are not universal constants but local features, determined by the birth of each cosmos. As speculative as these ideas may sound, they emerge from attempts to solve real puzzles in physics. Eternal inflation arises naturally from theories of the early universe. The string landscape is a prediction of efforts to unify fundamental forces. CPT symmetry is a cornerstone of quantum field theory. When combined, these strands point toward a reality far larger than our own universe, a reality where time itself may flow in different directions in different domains. The idea that universes might differ not only in their physical constants, but in their arrows of time, becomes clearer when we examine the role of symmetry in fundamental physics. At the deepest levels, nature often prefers balance. Symmetry principles guide the construction of theories, from the conservation of energy and momentum to the unification of forces. Among these, CPT symmetry stands out as especially powerful. It states that if we take any physical process and reverse three aspects at once, charge, parity, and time, the laws remain unchanged. Charge reversal means replacing every particle with its antiparticle, flipping positive charges to negative, and vice versa. Parity reversal means mirroring spatial coordinates, turning left into right. Time reversal means running the process backward. Taken together, CPT symmetry implies that the universe cannot distinguish between the original process and the transformed one. This principle is not just a conjecture, but a proven theorem within the framework of quantum field theory, the mathematical foundation that underpins the standard model of particle physics. What does this mean for time? It tells us that the laws of physics, at their most fundamental, treat both directions of time as equally valid. If matter moving forward in time is allowed, so is antimatter moving backward. If entropy can increase in one direction, then in principle, another system could exist in which entropy increases in the opposite direction, so long as charge and parity are also appropriately transformed. CPT symmetry opens the conceptual door to universes where the arrow of time is reversed, yet the underlying laws remain perfectly consistent. Experiments have tested these ideas in subtle ways. While CPT symmetry itself has never been violated, related symmetries have shown cracks. In the mid-20th century, physicists discovered that parity symmetry is violated in weak nuclear interactions. Later, experiments revealed that CP symmetry, the combination of charge and parity, is also broken in certain processes involving subatomic particles like kaons and B mesons. These violations are tiny, but they matter because they show that the universe does not treat matter and antimatter as perfect mirror images. The dominance of matter over antimatter in our universe may in fact be a consequence of such symmetry breaking. Yet even with CP violation, CPT symmetry remains intact. This resilience suggests that time reversal, while not directly observable in daily life, is deeply embedded in the structure of reality. If CPT holds universally, then for every universe with one arrow of time, there could exist a mirror counterpart with the opposite. In this sense, temporal symmetry is preserved not within a single universe but across the ensemble of all universes. The multiverse hypothesis magnifies this possibility. If eternal inflation spawns countless bubble universes, and if the string landscape provides a nearly infinite variety of initial conditions, then the multiverse may host not only different laws of physics but different temporal orientations. Some universes may begin smooth and low in entropy like ours, evolving forward. Others may begin in mirrored conditions, evolving backward. CPT symmetry ensures that both are allowed, while the mechanism of inflation provides the stage for their creation. For beings within such universes, the difference would not be apparent. Just as we remember our past and anticipate our future, they would remember what we call our future and anticipate what we call our past. Their psychological arrow would align with their entropy, just as ours does. The notion of reverse time only arises when comparing across universes, a perspective unavailable to any inhabitant. From within, each arrow feels natural and forward. This challenges our deepest intuitions about time. We often think of past and future as absolute, fixed directions built into the fabric of reality. But if CPT symmetry and the multiverse are correct, then past and future are relative, defined locally by initial conditions and entropy growth. The ultimate symmetry lies not in one universe but in the ensemble of all, where every arrow is represented. The possibility of universes with reversed arrows of time raises a natural question. Could such universes support life and complexity in the same way ours does? At first glance, the idea may seem absurd. How could organisms evolve, planets form, or stars burn if time itself ran backward? Yet this reaction arises because we instinctively project our arrow of time onto theirs. In reality, beings in a reverse time universe would not experience their world as backward. For them, entropy would increase in their direction of time, memories would accumulate along that axis, and radiation would propagate in ways consistent with their arrow. What looks like reversal to us would feel normal to them. The key lies in recognizing that complexity depends on gradients, not on direction. In our universe, life thrives because the sun provides a steady flow of energy, creating conditions far from equilibrium. Organisms harness this flow to build and sustain order. If a universe with reversed time had similar energy gradients, stars shining, planets warming, chemical processes unfolding, then life could also emerge. The direction of entropy would be reversed relative to ours, but from within, it would be indistinguishable. Complexity does not care about which way time points, only that conditions allow it to persist. This perspective helps dissolve the apparent paradox. The multiverse may host universes with different arrows, but each is internally consistent. Our sense of forward is simply tied to our entropy. Their sense of forward would be tied to theirs. There is no universal master clock dictating one true direction. Instead, time's arrow is local, defined by the history and boundary conditions of each cosmos. The multiverse frameworks of eternal inflation and the string landscape provide the mechanism, while CPT symmetry provides the theoretical foundation. Together, they paint a picture of reality in which time is not absolute but relative across universes. Some cosmologists argue that this vision may be the most natural way to reconcile the symmetry of fundamental laws with the asymmetry of experience. If the equations allow both directions equally, then perhaps the multiverse realizes both, ensuring balance on the grandest scale. Of course, these ideas remain speculative. We cannot observe other universes directly, nor can we verify their arrows of time. The evidence for the multiverse is circumstantial, rooted in theories that themselves are not yet proven. Eternal inflation is consistent with what we see but remains unconfirmed. The string landscape is vast and mathematically complex, with predictions difficult to test. CPT symmetry is robust, but its cosmological implications remain theoretical. Scientific humility demands that we treat these possibilities as hypotheses, not established fact. Yet speculation in physics has a purpose. It pushes us to confront puzzles that otherwise remain unresolved. The origin of time's arrow is one such puzzle. Why was the early universe so low in entropy? Why do the laws of physics permit reversibility, while our experience insists on irreversibility? Multiverse hypotheses provide one path toward resolution, suggesting that our arrow is just one of many, realized in a cosmos far larger than we can see. As we step back from this vast picture, the implications for our place in the universe become clear. Time is not an absolute flow imposed by nature. It is an emergent property tied to the conditions of our world. Our sense of forward is not unique, but one of many possible orientations. Other universes may exist where the arrow points differently, and to their inhabitants, that direction would feel just as real as ours. The question then is not whether time runs forward or backward, but how the laws of physics, combined with initial conditions, create the arrows we experience. The multiverse suggests that both directions are possible, realized across different domains. To explore these possibilities further, we must turn to the quantum realm, where time, symmetry, and retrocausality emerge most vividly. It is here, in the strange behavior of particles and waves, that the deepest questions about time find their sharpest expression. The quantum world has always challenged our understanding of time. On the surface, the equations of quantum mechanics are perfectly time-symmetric. The Schrödinger equation, which governs how a wave function evolves, remains valid whether we let time run forward or backward. If we replace time with negative time, the mathematics works just as well. This symmetry suggests that at its most fundamental level, quantum physics does not care about the arrow of time. Yet when we step into the realm of measurement, the situation becomes more complex, and it is here that questions about retrocausality arise. Richard Feynman offered one of the most striking interpretations of quantum symmetry. In his work on quantum electrodynamics, he showed that the mathematics describing an antiparticle moving forward in time is identical to that of a particle moving backward in time. For example, a positron, the antiparticle of the electron, can be thought of as an electron traveling into the past. This is not a poetic metaphor, but a rigorous mathematical equivalence. It means that the equations of quantum physics permit time reversal in a very literal way, blurring the line between what we call past and future. The strange possibility of particles moving backward in time connects directly to retrocausality, the idea that future events might influence the past. Quantum mechanics already presents us with scenarios that seem to defy classical causality. In the famous double-slit experiment, a particle behaves like a wave, passing through both slits at once and interfering with itself. But when we observe which slit it goes through, the interference disappears, as if the particle's past behavior depends on our present choice of measurement. This peculiar feature has led some physicists to consider whether quantum mechanics allows information to flow backward in time, at least at the microscopic level. One of the most daring proposals was the Wheeler-Feynman absorber theory, developed in the mid-20th century. In this model, electromagnetic radiation is not simply emitted and then absorbed. Instead, it involves a handshake between the past and the future. An emitter sends a wave both forward and backward in time, and an absorber responds, completing the interaction. What we experience as radiation traveling forward in time is, in this view, the result of a two-way exchange between emitter and absorber across time. While this theory remains controversial, it captures the essence of retrocausality, the idea that the future can reach back to shape the past. Other experiments also raise questions about causality. In delayed choice experiments, first proposed by John Wheeler, a particle seems to decide whether to behave as a wave or as a particle, depending on a measurement performed after it has already passed through a slit. In some versions of the experiment, the choice of measurement appears to determine the particle's past. Though the outcomes are always consistent with the standard rules of quantum mechanics, they suggest that our classical intuition about cause preceding effect may not hold at the quantum level. These possibilities highlight a key tension. Quantum mechanics is time-symmetric in its equations, but time-asymmetric in its interpretation. The wave function evolves reversibly, yet measurement introduces irreversibility. We can describe a particle's state backward in time, yet when we observe it, we see a one-way process. Some physicists argue that this asymmetry is not fundamental but a reflection of how we interact with the quantum world. Others suggest that it reveals a deeper feature of reality, one in which retrocausality plays a genuine role. The quantum domain, therefore, opens the door to imagining universes where time's arrow is not fixed but fluid, where particles move both forward and backward in time, and where causality itself may be relative. This challenges not only physics but also philosophy, forcing us to ask what it means for an event to cause another. Does causality flow only in one direction, or is it a construct shaped by entropy and observation? As we move deeper into this chapter, we will explore how quantum mechanics, retrocausality, and time symmetry connect, and how these ideas push the limits of what we can know about the flow of time itself. Quantum mechanics invites us to reconsider some of the deepest assumptions about time. When Richard Feynman described antiparticles as particles moving backward in time, he was not merely offering a philosophical metaphor, but presenting a precise, mathematical interpretation. In Feynman diagrams, which are graphical representations of particle interactions, an electron traveling forward in time looks identical to a positron traveling backward in time. This equivalence means that the flow of time, which feels so absolute in daily life, is flexible in the quantum realm. Particles and antiparticles are two sides of the same equation, distinguished only by the temporal direction in which they are described. This insight reshaped our understanding of matter and antimatter. When Paul Dirac first predicted the existence of the positron, he derived it from solutions to his equation that initially seemed unphysical. But with Feynman's interpretation, those solutions became natural. They were simply the mirror images of ordinary particles, obeying the same rules, but moving in the opposite temporal direction. In experiments, we never perceive positrons as time travelers, but the mathematics shows that such an interpretation is valid. The backward flow of time is encoded in the very equations that describe the quantum world. Building on these ideas, the Wheeler-Feynman absorber theory attempted to explain radiation in terms of time symmetry. In classical electrodynamics, when a charged particle accelerates, it emits radiation that travels forward in time. But Maxwell's equations also allow advanced solutions, waves that travel backward in time. The absorber theory proposed that both solutions are real. An emitter sends radiation both forward and backward, and an absorber, in the future, responds by sending waves back. The result is a complete handshake across time, ensuring that radiation is fully accounted for without the need for arbitrary assumptions. Although the absorber theory is not widely accepted as the definitive description of electromagnetic processes, it illustrates the radical possibilities inherent in quantum mechanics. If radiation can involve both future and past, then time itself becomes a two-way street at the most fundamental level. For us, locked into the thermodynamic arrow, only the forward component is visible, but the equations whisper of a deeper symmetry, one in which cause and effect are less rigid than they appear. Experiments in quantum optics strengthen this impression. John Wheeler's delayed choice experiment, first proposed in the 1970s, asks whether a photon behaves as a wave or as a particle when passing through a pair of slits. If we decide to measure which slit it takes, the interference pattern disappears, and the photon behaves like a particle. If we choose not to measure, the interference remains, and the photon behaves like a wave. The astonishing twist is that the decision of what to measure can be made after the photon has already passed the slits. It is as if the photon's past behavior depends on a future choice. More recent variations, such as quantum eraser experiments, take this strangeness even further. In some setups, information about a photon's path can be erased after it has been detected, restoring interference patterns retroactively. These experiments do not allow us to send signals backward in time, but they do reveal that the quantum world does not conform to the strict causal order we expect. The future seems to influence the past, at least in how outcomes are recorded and interpreted. This blurring of temporal order challenges the idea that causality is fundamental. Perhaps causality, like the arrow of time itself, is emergent. It may arise from the growth of entropy and the macroscopic irreversibility that shapes our perceptions. At the microscopic level, events may not be chained together in a simple forward sequence. Instead, they may form a web of correlations that extend across time in both directions. The implications for time symmetry are profound. If quantum processes can involve retrocausality, then the existence of universes with reversed arrows of time becomes less fantastical. The same equations that describe our world also permit worlds where the flow of time is flipped. Quantum mechanics does not forbid it. On the contrary, it provides mechanisms that hint at how such reversals could be realized. As we look deeper into these quantum mysteries, the boundary between past and future begins to blur. What feels absolute at our scale may be contingent at the smallest scales. The flow of time may be less a river carrying events forward than a tapestry woven from both directions, with threads stretching from the past into the future and from the future back into the past. The strange hints of retrocausality in quantum mechanics have inspired decades of debate. On one side are those who see these experiments and interpretations as evidence that the future can genuinely influence the past. On the other side are those who argue that retrocausality is more a feature of how we describe quantum processes than of nature itself. Whichever view one takes, the fact remains that the mathematics of quantum theory treats time with perfect symmetry. The Schrödinger equation, the Dirac equation, and the principles of quantum field theory all allow time to run in either direction without contradiction. Yet when we step into the world of measurement and observation, time appears to favor one direction. A quantum system in superposition evolves reversibly until it interacts with its environment. At that moment, decoherence occurs, correlations spread, and the system takes on a definite outcome. This process looks irreversible, like an arrow embedded within quantum mechanics itself. But many physicists argue that even this irreversibility is not fundamental. Decoherence is simply the entanglement of systems with their surroundings, and in principle, it could be reversed if every microscopic degree of freedom were controlled. Once again, it is the practical impossibility of reversal, not a law forbidding it, that creates the arrow we perceive. This perspective aligns quantum mechanics with the thermodynamic view of time. Just as entropy increase arises from probability and initial conditions, so does quantum irreversibility. The apparent collapse of the wave function is not a cosmic decree, but an emergent feature of interactions in a universe that began in low entropy. The psychological arrow, the thermodynamic arrow, and the quantum arrow all converge because they are built on the same statistical foundation. Still, the possibility of retrocausality remains a live topic. Some interpretations of quantum theory, such as the transactional interpretation proposed by John Cramer, embrace time symmetry explicitly. In this model, quantum events involve both retarded waves traveling forward in time and advanced waves traveling backward. An emitter and an absorber exchange signals across time, creating a handshake that determines the outcome. Though not widely accepted, this interpretation provides a vivid picture of how retrocausality could operate without contradicting experiment. Other physicists explore the role of time symmetry in quantum cosmology. If the universe itself is a quantum system, then perhaps its wave function evolves in both directions from the Big Bang, with arrows of time pointing away from the origin. In this view, retrocausality is not a strange exception, but a natural consequence of the symmetry of the whole. Our universe and a mirror counterpart could both arise from a single quantum state, each with its own forward-moving arrow, yet opposite in orientation. Despite these possibilities, most working physicists remain cautious. Retrocausality does not provide a practical mechanism for sending information to the past. All experiments remain consistent with the rule that signals cannot travel faster than light and cannot reverse causality in a way that would produce paradoxes. The strange correlations revealed in delayed choice and quantum eraser experiments do not allow us to rewrite history. They simply reveal that the quantum world is not bound by the same intuitive notions of cause and effect that govern the macroscopic world. In the end, quantum mechanics reinforces the central theme of this book. The fundamental laws of physics are time-symmetric, allowing processes to unfold forward or backward without contradiction. The arrow of time emerges only when we consider boundary conditions, entropy, and the limitations of observation. Retrocausality, whether literal or interpretive, serves as a reminder that our everyday sense of temporal order is not absolute. It is an emergent property of a universe that began in a special state and has been evolving probabilistically ever since. As we close this chapter, we stand at the threshold of deeper mysteries. Quantum mechanics shows us that time's direction is not built into the equations, but into the history of the cosmos. It hints that universes with reversed arrows are not only possible but natural extensions of the same mathematics. To see how these possibilities play out on the grandest scales, we must now turn to black holes, where the meeting of gravity, entropy, and quantum theory pushes the question of time to its most extreme. If there is any place in the universe where time itself might bend, break, or even reverse, it is in the presence of black holes. These extraordinary objects, born from the collapse of massive stars or the mergers of smaller black holes, represent the most extreme manifestations of gravity. In them, matter is crushed into a region so dense that not even light can escape. Black holes are often described as boundaries of no return, where the known laws of physics are pushed to their limits. They are also central to the question of time's arrow, because they embody both the increase of entropy and the possibility of symmetry at the edge of space-time. The connection between black holes and entropy was first uncovered in the 1970s, when Jacob Bekenstein and Stephen Hawking made a revolutionary discovery. They showed that black holes are not simply gravitational traps, but thermodynamic systems. A black hole has entropy, proportional to the area of its event horizon, and temperature, associated with the faint radiation it emits. This was astonishing, because it linked gravity, thermodynamics, and quantum theory in a single framework. Hawking radiation, as it became known, arises from quantum effects near the event horizon, where particle-antiparticle pairs form, and one escapes while the other falls in. Over time, this process causes the black hole to lose mass and eventually evaporate. From the standpoint of entropy, black holes are extreme objects. Their entropy is enormous, dwarfing that of ordinary matter. A single black hole can contain more entropy than all the stars in a galaxy. This means that when matter collapses into a black hole, entropy increases dramatically, consistent with the second law of thermodynamics. Far from violating the arrow of time, black holes reinforce it. They act as engines of entropy growth, pushing the universe closer to equilibrium. Yet black holes also reveal paradoxes that touch on time symmetry. The most famous is the information paradox. If a black hole evaporates completely through Hawking radiation, what happens to the information about the matter that fell in? According to quantum mechanics, information cannot be destroyed. The wave function of the universe evolves deterministically and reversibly. But if a black hole swallows information and then disappears, the process appears irreversible. This conflict between quantum mechanics and general relativity strikes at the heart of our understanding of time. Some physicists suggest that the information is preserved, encoded in subtle correlations in the Hawking radiation. Others argue that it might be stored on the event horizon itself, in what is known as the holographic principle. This principle, inspired by black hole physics, suggests that the information content of a region of space is proportional not to its volume, but to its surface area. If true, it means that black holes are not ultimate destroyers of information, but keepers of it, consistent with time's symmetric laws. The singularity at the core of a black hole raises even more extreme questions. According to general relativity, the collapse of matter leads to a point of infinite density where space-time curvature becomes infinite. At such a singularity, the equations break down. Time as we know it may cease to exist. Some theoretical models suggest that time could even reverse beyond the singularity, with the collapse leading to a bounce into another universe, where the arrow of time points the opposite way. While this idea remains speculative, it highlights how black holes serve as laboratories for thinking about time symmetry at the deepest levels. At the boundary of a black hole, the event horizon marks a point of no return. From the perspective of an outside observer, time appears to slow as an object approaches the horizon. To the infalling object, however, time flows normally until the singularity is reached. This divergence of perspectives illustrates the relativity of time itself. Near a black hole, the simple division between past and future becomes blurred. The very concept of time is stretched to its breaking point. Black holes, therefore, embody a paradoxical relationship with the arrow of time. On the one hand, they are engines of entropy growth, reinforcing irreversibility. On the other, they raise questions about information, preservation, and singularities that challenge our understanding of temporal symmetry. They are both the guardians of the arrow and the gateways to its possible reversal. The discovery that black holes possess entropy and temperature was one of the most profound insights of 20th century physics. Jacob Bekenstein first argued that if black holes obey the laws of thermodynamics, they must have entropy proportional to the surface area of their horizons. Stephen Hawking soon confirmed this with a detailed calculation, showing that quantum effects near the event horizon produce radiation. This Hawking radiation means that black holes are not perfectly black. They glow faintly, radiating energy in a way consistent with having a temperature. The implications are staggering. Black holes, once thought to be simple voids, are revealed as thermodynamic systems. Their entropy is proportional to the area of the event horizon, not the volume within. This finding led to the holographic principle, which proposes that the information content of any region of space is encoded on its boundary surface. In this way, black holes bridge the gap between gravity, quantum mechanics, and statistical mechanics, disciplines that otherwise seem worlds apart. The entropy of a black hole is immense. A black hole with the mass of the Sun has an entropy many orders of magnitude greater than the Sun itself. This means that when matter falls into a black hole, the entropy of the universe increases dramatically. Far from threatening the second law of thermodynamics, black holes uphold it on a cosmic scale. They serve as entropy sinks, steadily increasing the disorder of the universe as they swallow matter and radiation. The arrow of time is safe, or so it seems. Yet Hawking's calculation also raised the famous information paradox. If black holes radiate away their mass and eventually evaporate, what happens to the information about the particles that fell in? According to quantum mechanics, the evolution of a system is unitary, meaning information is preserved. The Schrödinger equation does not allow destruction of information, but if black hole evaporation erases the details of what entered, then quantum mechanics appears to break. This tension between unitarity and evaporation is one of the central unsolved problems in physics. Many solutions have been proposed. One possibility is that information escapes slowly, encoded in subtle correlations within the Hawking radiation. Though each photon looks random, the full set of emitted particles might carry a hidden pattern that preserves information. Another idea is that information is stored on the event horizon itself, like data etched on a cosmic screen. This is the essence of the holographic principle, which suggests that the universe at large may function in a similar way, with the three-dimensional bulk encoded on two-dimensional boundaries. Whichever resolution is correct, the key point is that time symmetry is at stake. If information is destroyed, then processes in black holes are fundamentally irreversible, contradicting the reversible nature of quantum mechanics. If information is preserved, then even the most extreme processes in the universe remain consistent with time-symmetric laws. The outcome will shape our understanding not only of black holes, but of time itself. The paradox also highlights the subtlety of entropy. From the outside, a black hole seems to erase the distinctions among the things it swallows. A book, a planet, or a cloud of gas all become indistinguishable once inside. The event horizon hides their details, replacing them with a single number. entropy proportional to area. Yet if information is preserved, then these distinctions are not truly lost. They are encoded in ways we do not yet fully understand. The universe, it seems, refuses to let go of its history entirely. Black holes therefore represent both the triumph and the challenge of the arrow of time. They maximize entropy growth, reinforcing irreversibility on a cosmic scale. Yet they also pose the possibility that time-symmetric laws might still govern the deepest processes, hidden beneath horizons and cloaked by radiation. They stand at the boundary between what we know and what remains mysterious, pointing to a deeper unity that may reconcile gravity and quantum mechanics. At the heart of every black hole lies a singularity, a point where general relativity predicts that density and curvature become infinite. In practice, physicists believe this singularity signals the breakdown of the theory itself. Einstein's equations cannot describe conditions of such extremity. To understand what really happens inside, we will need a theory that unites gravity and quantum mechanics. Until then, the singularity remains an enigma, a boundary where our knowledge of time itself may fail. Speculation about what lies beyond the singularity often touches on the possibility of time reversal. Some models suggest that collapse could lead to a bounce, creating a new, expanding universe on the other side. In such a scenario, the arrow of time inside the new universe might point away from the singularity, opposite to the arrow in ours. From this perspective, black holes could be cosmic gateways, where time does not end, but reorients. While no direct evidence exists for this idea, it illustrates how singularities force us to reconsider the absoluteness of temporal direction. Wormholes, hypothetical tunnels through space-time, also raise tantalizing questions. If a black hole connects to a white hole, a theoretical object that expels matter, instead of swallowing it, then information might pass through, preserving time symmetry across regions. White holes have never been observed, and many physicists doubt they exist. Yet, their mathematical possibility reminds us that the equations of general relativity are not biased toward one arrow of time. They allow structures that invert or redirect it, even if nature does not realize them in practice. From the perspective of an outside observer, time behaves strangely near a black hole. As an object falls toward the event horizon, its motion appears to slow, asymptotically freezing at the edge. To the falling object, however, time flows normally, carrying it swiftly toward the singularity. This divergence of perspectives shows that time is not a universal rhythm, but a local experience, shaped by gravity. In extreme cases, the familiar line between past and future becomes blurred, reminding us that our intuitive sense of time is not absolute. The entropy of black holes also points toward the ultimate fate of the cosmos. If black holes dominate the distant future, swallowing stars and galaxies, then the universe will become a sea of high entropy, punctuated by evaporating horizons. As they radiate away their mass, entropy continues to rise, pushing the cosmos toward equilibrium. In this far future, the arrow of time may lose its meaning, as the universe approaches a state where no further change is possible. Black holes thus not only shape the arrow of time today, but may also define its end. In many ways, black holes are paradoxical symbols of time. They are engines of irreversibility, consuming matter and raising entropy to staggering heights. Yet they may also be places where time symmetry reasserts itself, preserving information in ways we cannot yet fully see. They reveal both the strength and the limits of our current theories, forcing us to imagine new frameworks in which gravity and quantum mechanics are united. Above all, they remind us that time is not a simple flow but a feature of the universe still waiting to be fully understood. As we leave this chapter, one lesson stands out. Black holes are not just astronomical curiosities, but profound laboratories for the study of time. They reinforce the arrow, magnify entropy, and yet hint at deeper symmetries hidden beneath the surface. If time can bend, reverse, or split into different arrows, black holes are where we are most likely to glimpse it. From here, the question becomes whether the symmetries revealed in black holes are also written into the laws of fundamental physics. a question that will guide us into our next exploration. When physicists study the fundamental laws of nature, they often find that the deepest patterns are not in the details of individual particles, but in the symmetries that govern them. Symmetry tells us that physical laws remain the same under certain transformations. Rotate an experiment 90 degrees, and the outcomes are unchanged. Shift the entire setup to another place in space, and the results remain the same. These symmetries are not just aesthetic, they lead directly to conservation laws, like the conservation of energy and momentum. Among all symmetries, one of the most profound is time reversal. If we take the equations of physics and replace time with its negative, the mathematics continues to hold. This symmetry is formalized in what is known as the CPT theorem. In the framework of quantum field theory, which underpins the standard model of particle physics, CPT symmetry is guaranteed. It states that if we reverse charge, flip spatial coordinates, and reverse time simultaneously, the laws of physics remain exactly the same. No experiment has ever found a violation of CPT. This makes it one of the most trusted principles in physics. As foundational as the conservation of energy, time reversal symmetry alone, however, is more subtle. While the equations often allow it, not every process looks symmetric in practice. One striking example comes from the violation of CP symmetry, the combination of charge, reversal, and parity. In the 1960s, experiments with neutral kaons showed that the laws of physics are not perfectly symmetric under CP. Later studies with B mesons confirmed similar violations. These tiny asymmetries suggest that time reversal symmetry must also be violated in certain processes, because CPT, as a whole, must remain exact. If CP is broken, then T must be broken as well to preserve the overall balance. The importance of these violations cannot be overstated. Without them, matter and antimatter would have been created in equal amounts in the early universe, annihilating each other completely and leaving nothing behind but radiation. The small asymmetry favoring matter ensured that some of it survived, forming the galaxies, stars, and planets we see today. In this sense, our very existence depends on the subtle breaking of time reversal symmetry at the level of fundamental particles. At first glance, this seems to challenge the idea that time's arrow is merely emergent. If time reversal symmetry is violated, does that not mean time has a preferred direction built into the laws themselves? The answer is more nuanced. The observed violations occur in very specific conditions involving the weak nuclear force. They do not provide a universal arrow of time like entropy does. Instead, they reveal that at the smallest scales, nature has a slight tilt, a preference that breaks perfect symmetry. The overall equations still allow time reversal in most cases, but in certain rare interactions, the balance is shifted. These results remind us that time symmetry is not a simple yes or no question. It holds broadly across physics, but with exceptions that play a crucial role in shaping the universe. At the macroscopic level, the arrow of time is dominated by entropy, overwhelming in its statistical certainty. At the microscopic level, time symmetry is nearly exact, but broken in subtle ways that explain why matter dominates over antimatter. The two perspectives are not in conflict but complementary, each revealing a different aspect of temporal reality. The study of time reversal in theoretical physics therefore bridges the gap between the abstract beauty of symmetry and the concrete reality of the cosmos. It shows us that while time reversal is deeply embedded in the laws of nature, it is not absolute. Tiny violations remind us that even the most elegant symmetries can be bent by the workings of the universe, and in those bends, entire galaxies and civilizations find their origin. Time reversal in theoretical physics is not just a matter of elegant equations, it is also a matter of experiment, of putting nature to the test, and asking whether time truly treats every process the same. The discovery of CP violation in the 1960s was a turning point. Until then, most physicists assumed that the laws of physics were symmetric under charge and parity combined. The observation that neutral kaons decayed in ways that violated CP symmetry came as a shock. It was the first hint that the universe is not perfectly balanced, and that at the most fundamental level, symmetry can be broken. Later experiments with B mesons confirmed this asymmetry, showing that it is not unique to kaons, but a feature of weak interactions more generally. These results imply that if CP symmetry is violated, then time reversal symmetry must also be violated, because CPT as a whole remains exact. This conclusion has been tested directly. In 2012, researchers working with the Babar experiment at the SLAC National Accelerator Laboratory announced the first direct observation of time reversal violation. By carefully studying the transitions of neutral B mesons, they showed that the probability of a process running forward was not equal to the probability of its time-reversed counterpart. This was a historic confirmation that time reversal symmetry is not perfect. What does this mean for the arrow of time? On the surface, it might seem that physics has found a fundamental direction built into the laws themselves. But the violations observed are incredibly small, limited to specific interactions in the weak nuclear force. They do not dictate the macroscopic arrow that governs our daily experience. Instead, they reveal that time symmetry is nearly exact, but not absolute. The universe has a subtle preference, a tilt that becomes crucial when extrapolated to the early cosmos. This tilt may help explain why matter dominates over antimatter. If the laws of physics were perfectly time-symmetric, the Big Bang would have produced equal amounts of both, which should have annihilated one another, leaving only photons. The fact that matter survived to form galaxies, stars, and people suggests that some asymmetry favored matter, CP violation, and with it time reversal violation, provides a mechanism for this imbalance. Though the details remain incomplete, these tiny effects may have tipped the scales, giving rise to everything we know. In this sense, the breaking of time reversal symmetry at the microscopic level is not the same as the thermodynamic arrow, but is equally essential. The thermodynamic arrow arises from entropy and probability, shaping our everyday perception of time. The microscopic breaking of symmetry explains why the universe contains matter at all. Without it, there would be no arrow for us to perceive, no observers to wonder about the flow of time. The search for time reversal violation continues. Experiments with neutrinos, particles that barely interact with matter, may hold further clues. Neutrinos are suspected to exhibit CP violation, and if confirmed, this could provide additional evidence for time asymmetry in fundamental physics. Precision experiments at particle accelerators aim to measure these effects with increasing accuracy, probing the boundaries of symmetry at the smallest scales. The broader lesson is that time reversal in theoretical physics is not an all-or-nothing concept. Symmetry holds as a guiding principle, but nature permits exceptions. These exceptions, though small, have profound consequences. They shaped the early universe, determined the balance of matter and antimatter, and set the stage for galaxies and life. Time's arrow is not dictated solely by entropy or solely by symmetry breaking, but by the interplay of both, woven together across scales from the quantum to the cosmic. The study of time reversal in theoretical physics teaches us as much about the limits of our knowledge as it does about the laws themselves. CPT symmetry remains one of the most reliable principles in all of physics. Every experiment designed to test it has confirmed its validity. No violation has ever been observed, despite the extraordinary precision of modern particle accelerators. This robustness tells us that, at its foundation, the universe is deeply symmetric. Yet, the cracks in CP symmetry and the corresponding hints of time reversal violation remind us that perfection is not absolute. Nature allows subtle exceptions, and those exceptions shaped the very existence of matter. Still, the observed violations are small, and they do not replace the thermodynamic arrow of time. They do not explain why entropy increases, why coffee cools, or why we remember yesterday, but not tomorrow. They only explain why matter exists at all. Without these tiny asymmetries, our universe would be lifeless, filled with nothing but radiation. With them, matter survived, galaxies formed, and the arrow of time, defined by entropy, had a stage upon which to unfold. The two perspectives, symmetry breaking and entropy, are not in competition, but in partnership. Together, they explain why time has both a microscopic tilt and a macroscopic flow. Current research continues to probe the boundaries of time reversal. Experiments with neutrinos are among the most promising. These elusive particles, created in nuclear reactions in stars and reactors, may violate CP symmetry in ways not yet fully measured. If they do, this would strengthen the connection between microscopic time asymmetry and the cosmic matter-antimatter imbalance. Other tests search for electric dipole moments in particles such as the neutron. A non-zero electric dipole moment would signal violation of time reversal symmetry. So far, none has been observed, but experiments are pushing the limits of sensitivity ever further. The search is not merely academic. Each new measurement tests the fabric of the universe at its most fundamental level. If CPT symmetry were ever found to fail, it would shake the foundations of quantum field theory and demand an entirely new framework. If additional sources of time reversal violation are discovered, they could provide the missing pieces needed to explain why our universe looks the way it does. Time, it seems, remains both the most familiar and the most mysterious dimension, and its study demands both humility and persistence. For the question of reversed universes, these findings are crucial. If time reversal is not absolute, but nearly so, then the idea of universes with arrows pointing in opposite directions remains entirely plausible. The laws permit it, the symmetries allow it, and the small asymmetries we observe remind us that directionality is not fundamental, but emergent. Our arrow is not the universe's decree. It is one possibility among many, shaped by both symmetry and its breaking. As we close this chapter, the picture becomes clearer. Time reversal is deeply embedded in theoretical physics, guaranteed by CPT symmetry, yet punctuated by rare violations that give rise to our existence. These results connect the smallest scales of particle interactions with the largest scales of cosmic history. They show that time's arrow is not a single concept but a layered phenomenon, emerging from both entropy and symmetry breaking. And they prepare us for the final stage of our exploration, where science meets philosophy, and we ask what it truly means for time to run backward, not just in equations, but in experience. Physics gives us equations, symmetries, and probabilities, but the question of time cannot be confined to physics alone. Time shapes not only the cosmos, but also the human experience of reality. To ask what it would mean for time to run backward is to step into philosophy, where questions of causality, perception, and existence take center stage. Here, the focus shifts from what the equations allow to what it means for beings like us to live in a universe where arrows of time might point differently. One of the deepest questions is whether causality itself depends on entropy. In our universe, causes precede effects. We strike a match, and a flame appears. We speak words, and sound waves ripple outward. This order feels so fundamental that it is hard to imagine it being otherwise. Yet causality may not be a primary law. It may instead be a reflection of the thermodynamic arrow. When entropy increases, traces are left behind. These traces allow us to identify causes and effects. The flame leaves smoke, the sound leaves echoes, the past leaves memory. If entropy were to decrease, then perhaps the direction of causality would also flip, with effects preceding causes in a way that would feel natural to inhabitants of that universe. This possibility forces us to consider whether causality is universal or relative. Philosophers have long debated this. In the block universe model, time is treated as another dimension, like space. Past, present, and future all exist simultaneously, and the flow of time is an illusion created by consciousness. In such a model, causality is not a fundamental feature of the universe, but an emergent property of how events are ordered along the arrow of entropy. Eternalism, the philosophical position associated with the block universe, holds that the future already exists, just as the past does. Presentism, by contrast, insists that only the present is real. Both perspectives wrestle with the implications of physics, where the equations are time-symmetric and the arrow of time arises from boundary conditions. For beings living in a universe with reversed time, these philosophical debates would take on a different flavor. They would not experience their world as backward. Their memories would align with their arrow of entropy, their causes would precede their effects, and their language would encode the same logic we use. From within, everything would feel natural. It is only from outside, from a comparison with our universe, that we would say their time runs the other way. This raises a subtle but profound point. The experience of time's direction is relative, not absolute. There is no cosmic compass pointing to the one true future. There are only arrows defined by conditions, each valid within its own universe. Philosophers also ask whether determinism holds in such scenarios. If the laws of physics are reversible, then in principle, the state of the universe at any one moment determines both its past and its future. This suggests that the flow of time is an illusion and that the universe is a fixed block of space-time. But if entropy and probability define the arrow, then the future may not be fully determined in practice. Instead, it may emerge as a statistical unfolding, with probabilities guiding outcomes. Retrocausality in quantum mechanics complicates this further, hinting that the relationship between past and future may be more entangled than we realize. The philosophical implications are staggering. If causality is not fundamental, if time is relative, and if determinism is statistical rather than absolute, then our everyday sense of reality is a fragile construction. We live inside a perspective shaped by entropy, memory, and observation. Change the arrow, and the perspective changes too. To ask what reverse time would mean is to ask what it means to exist at all. Philosophical discussions about time often circle back to the question of free will. If the universe is deterministic, unfolding according to equations that work equally well forward and backward, then perhaps the future is already written. In the block universe view, our lives are like paths traced on a four-dimensional map of space-time. We feel as though we are making choices, but in reality, every event from the formation of galaxies to the words spoken in this moment is already embedded in the fabric of existence. The flow of time is a feature of perception, not of the cosmos itself. For many, this picture is unsettling. If the future already exists, then are we truly free, or are we passengers in a predetermined story? Physics does not provide an easy answer. While classical mechanics suggests determinism, quantum mechanics introduces probabilities. The evolution of the wave function is deterministic, but the outcomes of measurements appear random. Some interpretations resolve this by suggesting that all possible outcomes occur in parallel branches of reality, while others argue that probabilities reflect genuine unpredictability in nature. In either case, the block universe remains consistent with the mathematics, even if it conflicts with our intuitive sense of free will. Now consider a universe with reverse time. Would its inhabitants have free will? From within, they would perceive themselves as making choices, just as we do. Their decisions would shape what they call their future, even if, from our perspective, that future aligns with what we call the past. If the block universe model is correct, then their story, like ours, would already be written across space-time. The difference is only in orientation. What we label backward would, for them, feel forward. Free will in such a cosmos would be as mysterious and contested as it is in ours. Another philosophical debate concerns the nature of the present. Presentism argues that only the present moment exists, while eternalism holds that past, present, and future are equally real. A third view, called the growing block universe, suggests that the past and present exist, but the future does not yet. Physics, with its time-symmetric equations, leans toward eternalism because nothing in the laws distinguishes the present from the past or the future. Yet our experience insists on the uniqueness of now, the flowing instant in which we live. In a reverse time universe, the tension between experience and physics would be no different. Its inhabitants would still experience a present moment, flowing along their arrow of entropy. They would still debate whether the past, present, and future all exist simultaneously, or whether only the present is real. These philosophical questions are not tied to the direction of time, but to the structure of consciousness itself. What changes is only the orientation of the arrow, not the depth of the mystery. Perception adds another layer. Neuroscience shows that memory is built from physical traces in the brain, stabilized by synapses and chemical changes that depend on irreversible processes. This ties the psychological arrow of time directly to entropy. In a reverse time universe, memories would accumulate in alignment with that cosmos's entropy, anchoring perception to its arrow. To its inhabitants, their orientation would feel natural. They would not notice any reversal, because their entire experience of reality would grow from their own direction of entropy increase. From our standpoint, such a world would appear uncanny. We would say that its inhabitants remember the future and forget the past, that they see effects before causes. But from within, no paradox would be felt. Their sense of causality would be coherent, just mirrored. This relativity of perception underscores the point that time's arrow is not absolute. It is local, emergent, and tied to conditions. What we see as reversal is, to others, simply normalcy. These reflections remind us that philosophy and physics converge on the same lesson. Time is not a universal river flowing from a single past to a single future. It is an orientation shaped by entropy, symmetry, and perception. Our debates about free will, determinism, and the nature of the present apply equally well in universes with opposite arrows. Time may run differently elsewhere, but the questions it raises remain the same. If universes can exist where the arrow of time points in the opposite direction, then the final philosophical question is whether such a universe could ever be recognized as backward, either by its inhabitants or by us. The answer appears to be no. For the beings who live there, time would feel as natural and forward-moving as it does for us. Their psychological arrow would align with their thermodynamic arrow, just as ours does. Their memories would accumulate in what they call the past, their causes would lead to effects, and their language and logic would encode the same assumptions we make. Nothing in their experience would suggest that their universe is reversed. From our perspective, however, their cosmos would look uncanny. We would say that entropy decreases as their time progresses, that their memories point into our future, that radiation converges instead of spreading. But such descriptions arise only because we compare their arrow to ours. Without that comparison, there is no sense in which their world is backward. There is only the alignment of arrows within their reality. This reveals a profound relativity. Time's arrow is not universal, but local, bound to the conditions of a given universe. This insight changes how we think about the very meaning of time. We are used to treating the past as fixed and the future as open, but this distinction is tied to entropy. The past is fixed because it has left traces, while the future is open because it has not. In a reversed time universe, the roles would swap, yet the inhabitants would feel exactly the same way we do. Their fixed past would be our future, but for them, it would simply be the past. Their open future would be our past, but for them, it would simply be what is yet to come. The relativity of these concepts shows that the structure of time is not absolute, but contextual. Philosophical debates about determinism also shift under this lens. If time is symmetric at the level of equations, then the entire history of a universe is embedded in its space-time fabric. Whether the arrow points one way or the other, the block universe remains intact. The perception of flow is an emergent feature, not a fundamental property. For inhabitants of either universe, free will would feel the same, even if determinism holds in the background. What changes is not the nature of choice, but the orientation of the arrow that frames it. This leads to a humbling conclusion. Our sense of time, so central to existence, may not be a universal truth, but a parochial feature of our cosmic neighborhood. The direction we call forward is only one of many possible orientations allowed by physics. Other universes may follow other directions, and their inhabitants would be as convinced of their forward as we are of ours. Time is not a single absolute river, but a family of arrows, each rooted in entropy and initial conditions, each equally valid within its own frame. As we reflect on this, philosophy and physics converge on the same message. Reality is larger than our intuitions. The arrow of time we know is not inevitable, nor is it unique. It is one possibility among many, shaped by conditions beyond our control. To imagine universes with reversed arrows is not to indulge in fantasy, but to recognize the richness of what the laws of physics allow. Our task is to accept both the limits of our perspective and the vastness of possibility that lies beyond it. With this realization, we close the philosophical exploration of reverse time. We have seen that causality, memory, and perception all depend on entropy, that determinism and free will look the same in any arrow, and that no universe would appear reversed from within. What feels absolute is in fact relative, and what feels unique is in fact one among many. The final step is to ask how much of this we can truly know, where evidence ends and speculation begins, and how to live with the mysteries that remain. At the end of our exploration, we arrive at the boundaries of what science can explain. We have followed the arrow of time from thermodynamics and entropy to cosmology, from quantum mechanics to black holes, from particle symmetries to philosophical reflections. Each step has revealed that the direction of time is not a fixed decree, but an emergent property of conditions, probabilities, and histories. And yet, for all that physics has taught us, mysteries remain. Time itself, the dimension that frames every experience and every experiment, is not fully understood. The most important lesson is that our arrow of time is contingent. It depends on the low entropy beginning of the universe, the statistical certainty of entropy increase, the alignment of psychological and radiative arrows, and the small violations of symmetry that allowed matter to survive. If the conditions had been different, the arrow might have pointed the other way, and we would never have noticed. Other universes could exist with reversed arrows, and their inhabitants would find them as natural as we find ours. Physics allows this, but it does not prove it. Here lies the limit. Physics can describe what is possible, but it cannot always say what is real. The equations of mechanics, quantum theory, and relativity all allow time reversal. Thermodynamics and cosmology explain why our universe's arrow points forward. But whether other universes exist with opposite arrows, whether time reversal is realized elsewhere in reality, remains speculation. We can build models, test symmetries, and probe initial conditions, but we cannot step outside our arrow to confirm another. Even within our own universe, open questions remain. Why did the cosmos begin in such a low entropy state? Inflation provides part of the answer, but not all. CP violation explains why matter survived over antimatter, but the details are incomplete. Black holes raise paradoxes about whether information is preserved or destroyed, and no consensus yet resolves them. Quantum mechanics whispers of retrocausality, but whether this reflects reality or interpretation is still debated. Time remains the thread that connects these puzzles, and at the same time, the veil that conceals their resolution. For us, living within time, there may always be limits to what we can know. We cannot observe the Big Bang directly, only its faint afterglow in the cosmic microwave background. We cannot see beyond event horizons, only infer their properties from radiation and gravity. We cannot step into another universe to test its arrow. Our experiments reach further each decade, but the horizon of knowledge moves with us, always leaving some mysteries just out of reach. This is not a failure of science, but its strength. Science advances by distinguishing between what can be tested and what must remain speculative. To say that universes with reversed arrows are possible is to remain faithful to the mathematics. To say that they exist is to go beyond evidence. The line between possibility and reality is thin but vital, and respecting it is what gives science its power. Yet even within these limits, time teaches us something profound. It shows us that what feels absolute may be relative, what feels universal may be local, and what feels inevitable may be contingent. The arrow of time is not a law written into the fabric of equations, but a story written into the history of our universe. To recognize this is to recognize the fragility of our perspective and the vastness of what lies beyond it. One of the most striking features of scientific progress is that it often reveals new limits, even as it expands knowledge. The study of time exemplifies this pattern. Each breakthrough uncovers deeper puzzles. Thermodynamics explained why entropy increases, yet it left unanswered why the universe began in such a low entropy state. Relativity revealed the malleability of space-time, yet it offered no explanation for the quantum nature of gravity. Quantum mechanics provided astonishing accuracy in predictions, yet it left us with interpretations that seemed to stretch causality itself. Time, more than any other concept, exposes both the power and the boundaries of human inquiry. When physicists explore time reversal experimentally, they do so with precision instruments, colliding particles, and analyzing decay patterns with exquisite detail. CP violation in kaons and B mesons was discovered through such methods, and the search for symmetry breaking continues with neutrino oscillation experiments. Each of these probes adds a brick to our wall of knowledge, but the wall also casts a shadow, showing us where we cannot see. Experiments tell us what happens in our universe, not in hypothetical others. They tell us how symmetries break, but not why the universe began with such special conditions. Cosmology faces similar boundaries. Observations of the cosmic microwave background reveal that the early universe was astonishingly smooth, with only tiny fluctuations. Inflation explains how this smoothness arose, but whether inflation itself is the final story or just a chapter remains unclear. The multiverse hypothesis extends inflation to suggest a vast landscape of universes, each with different arrows of time. But the multiverse may be forever beyond direct observation. We can infer its possibility, but we cannot confirm its reality. This distinction marks one of the great limits of science, the difference between what can be modeled and what can be measured. Black holes provide another example. Hawking radiation is predicted by robust calculations, but it is so faint that no experiment has yet observed it directly. The information paradox is debated through mathematics and thought experiments, not through direct measurement. The holographic principle suggests that the universe itself may be encoded on a boundary, but evidence remains circumstantial. In all these cases, time plays the central role, shaping the paradoxes, but the resolution remains hidden. Even in quantum mechanics, the limits are evident. Experiments confirm the accuracy of the theory to astonishing degrees, yet they cannot tell us which interpretation is true. Do wave functions collapse? Does reality branch? Does retrocausality genuinely occur? Or is it only a way of speaking? Physics describes outcomes, but it does not resolve the metaphysical implications. The boundary between what we know and what we interpret is sharpest here, where time's symmetry meets human perception. These limits are not obstacles to despair, but guides to humility. They remind us that science is not about possessing all answers, but about knowing where the answers lie and how to approach them. The arrow of time is a perfect example. We know that it emerges from entropy, that it is tied to initial conditions, that it is nearly, but not perfectly symmetric at the smallest scales. We also know that the deepest questions why those initial conditions existed, whether universes with opposite arrows are real, may remain forever outside our reach. In this humility lies strength. To admit what we cannot know is to sharpen what we do know. The study of time has shown us how far science can reach, from the heat of stars to the birth of the cosmos, from the tiniest particles to the largest black holes. It has also shown us the horizon of mystery, the edge where speculation begins. Standing at that edge, we see not failure, but possibility, the chance that reality is stranger, richer, and more diverse than we can yet imagine. At the end of this journey, we arrive at the boundary between knowledge and wonder. Physics has revealed that the arrow of time we experience is not written into the laws themselves, but emerges from the conditions of the universe. Entropy increases, memories form, radiation spreads, and cause precedes effect because our cosmos began in a state of extraordinary order. Without that low entropy beginning, time might feel very different. With different conditions, it might even run the other way. Backward time universes remain consistent with the equations of physics. The laws are symmetric, allowing time to flow in either direction. Quantum mechanics permits particles to be described as traveling backward in time. Cosmology allows for universes born in pairs, with arrows pointing away from a shared origin. The multiverse hypothesis provides a stage where both orientations might be realized. None of this is pseudoscience. It is the honest extension of what physics already permits, yet none of it is proven. Here lies the central truth. Possibility does not equal reality. What we know is limited to our universe. We know that entropy rises here. We know that black holes magnify it, that CP violation gave matter an advantage, that the cosmic microwave background confirms a low entropy start. We know that experiments have tested time reversal and found it nearly exact, with tiny violations that shape the cosmos we inhabit. We know that the arrow of time is contingent, emergent, and not absolute. Beyond that, we cannot go. Backward time universes may exist, or they may not. Science gives us no final verdict. This uncertainty should not diminish the wonder, but deepen it. To recognize the limits of knowledge is not to surrender, but to respect reality as it is. The mystery of time invites humility. It reminds us that even in an age of particle colliders and space telescopes, there are questions that remain open, not because we have failed, but because they reach beyond what can be measured. To live with those mysteries is part of being human. And yet, even within our limits, time gives us meaning. The arrow that runs through our universe is the arrow of our lives. It carries us from birth to growth, from memory to hope, from history to possibility. It is the framework of existence, the stage upon which every story unfolds. We may not know why it points the way it does, or whether it points differently elsewhere, but we know that it carries us, moment by moment, into the unknown. In this sense, the study of backward time universes is not only about physics, but about perspective. It teaches us that what feels absolute is relative, that what feels inevitable is contingent, that what feels universal may be local. It opens our minds to the possibility that reality is larger than our experience, richer than our imagination, and more mysterious than our equations. To contemplate universes where time runs backward is to glimpse the vastness of what could be, and to return with a deeper appreciation for the arrow we live within. As we close, one reflection remains. Time's arrow is central to human experience, yet physics shows it may not be absolute. It is a story told by entropy, by symmetry, by the birth of the cosmos. Other stories may be told in other universes, with arrows pointing the other way. Whether we ever confirm them or not, the very possibility expands our sense of what it means to exist. We live in one universe, with one arrow, and that is enough to fill a lifetime with wonder. But to know that the laws permit others is to feel the humility and the grandeur of science, to recognize that reality is not only stranger than we imagine, but stranger than we can imagine.